Thank you very much, and good morning. I hope you are not too hungover from the party yesterday, or at least you are fit enough for some machine learning. Namely, we are going to discuss the intersection of natural language processing and recommendation systems. My name is Stiebellehner. I'm data scientist at Kraftwerks and also lecturer in statistics and digital marketing at some universities. Great. Before we dive straight into the actual topic of our talk, let me just cover some words about the company I'm working for, Kraftwerks. We are a Vienna-based artificial intelligence and software engineering company. We have our office right in the heart of Vienna in the 7th district, and we usually develop highly customized, individual, user-centric solutions that have some kind of artificial intelligence at the very core. And that really ranges from predictive maintenance to recommendation system and kind of everything in between. And that's already it with the company talk. Let's dive right into the actual topic, which is text embedding algorithms in recommendation systems. So as you can see, we will be discussing two very distinct topics, actually. On the one hand, natural language processing, and on the other hand, recommendation system. And in our final part, in part 3, we will see how these two fields actually come together to build a powerful hybrid filtering recommendation system that is powered by Word2Vec, which is probably, well, the most popular text embedding algorithm these days. Great. So our first part will be on natural language processing. NLP, as we also call it, has become a really ubiquitous technology, right? It's everywhere. It's in our pockets. It's in our living rooms. It has really conquered the world in the last decade. For example, when you think of voice assistants, right? There is Google's voice assistant. There is Siri. Also, more recently, Cortana and Alexa. Well, all these are powered by natural language processing. And actually, although they used to be quite bad, they have become quite decent at understanding human language in the past couple of years, right? But, well, the fact that they actually got decent is not something that we can take for granted, because this man-machine communication is actually quite complicated, right? And it's complicated for one key reason, and that's because humans use natural language to communicate. We use German, we use English, Spanish, whatever. And natural language at its very core is ambiguous. It's non-deterministic. For example, when I say, "that's sick," I could mean a variety of different things. I could mean that something or somebody is not feeling well. I could mean that something is terrible, but I could also mean that something is great, right? So you see, human language is ambiguous at the very core. And then on the other hand, you have machines. And while machines don't use natural languages, machines use artificial languages created by us to communicate, and these languages are, well, binary, and then C++ and any other programming language, basically. And as you probably know, if you've ever written a piece of code, well, code does what you write, right? It never does. There is no ambiguity in it. There is no non-deterministic behavior, but artificial languages, machine-readable languages, are fully deterministic in most parts. And there you can see this mismatch. Humans using ambiguous languages, machines using deterministic languages, and so we have this mismatch and we have difficulties communicating. That means we need a translator, right? We need somebody that takes our human language and makes it machine readable. And that's actually where natural language processing comes into play. Oh, sorry. Natural language processing really is a translator. It's basically, it uses tools from a very broad collection, from computer science, from statistics, from linguistics, to make human language input machine readable. That's what it does. But how does this actually work? Like, how does natural language processing actually make this ambiguous language something that computers can work with? Well, there are a variety of processes how this can work, but at the very core, all these processes, just convert text into numbers, because in the very end, well, computers have to deal with it, and as you know, computers are really good at doing maths. They can handle numbers quite well. That's why they are called computers, after all. A very simple example of how we can turn text into numbers is the bag of words model we see here. So in the bag of words model, what we do is we simply count word occurrences. We count how often does a word occur in a piece of text. So in this very small example here, we have 3 sentences, right? 3 distinct sentences, and then we just start counting how often does a word occur in each sentence, And that gives us this sparse matrix down here, or also table, you could name it. And in this table, each sentence is represented as a sparse numeric vector, and each word as well. That's the bag of words method. But, well, already it fails at this very simple example, because it's quite ignorant. When you look at the first two sentences, these two sentences say something entirely different. They have an entirely different meaning. You could even say, they mean the opposite. But our bag of words model actually tells us they are the same. They have the entirely same vectors. And that's because, well, as I said, the bag of words model is ignorant. It ignores a lot of things. It ignores word order. That's why it failed here. It ignores any kind of context, and it ignores grammar and many more things that are of true importance for us humans to understand the meaning of text, right? And so it fails to model what really matters to us humans to understand meaning, and that is semantics. Semantics is the relationship between words and symbols. And that's what it doesn't capture, but that's what constitutes meaning to us. So we see, if we want to make machines truly understand what we are saying, we need to find a method that captures semantics, that captures what is meaning to us humans. And, well, that's a complicated thing. How do we do that? It's not obvious, because semantics is something that is rather abstract. Well, it turns out that a genius linguist back in the 50s had an idea. And this was J.R. Firth, and he said, "You shall know a word by the company it keeps." And by that, he basically formulated the distributional hypothesis, which is really a key concept in distributional linguistics. And it says that words that appear in similar context are similar in meaning. That means, well, if two words are surrounded by usually the same words, you could say they are likely to have the same meaning, right? And, well, modern-day computer scientists thought about that. They thought, all right, so we have this distributional hypothesis, and it basically gives us a nice idea of how we can infer the meaning of a word. Now we just need to develop an algorithm that actually captures exactly this idea and generates some numerical representation from that. Well, and that's actually how text embedding algorithms were invented. And the most famous among them currently is inarguably Word2Vec, invented by Mikolov back in 2013, 2014. However, it's still state of the art. Back then, it was really a small revolution in NLP. And Word2Vec actually is a quite efficient algorithm that manages to encode semantics and to generate dense numeric vector representations for each word in our vocabulary. And these vectors, that we call word embeddings, encode the true meaning of a word. And that made it really feel like magic to people that saw this first. But actually, it's not magic, but as it is so often, it's just math, right? And what we can see here is the architecture of the neural network that is used for Word2Vec. And for completeness, let me mention that in the original Word2Vec paper, Mikolov proposed two different architectures, the skipgram architecture and the SIBO architecture. Here we will discuss only the SIBO architecture, which stands for continuous bag of words, just for, well, simplicity. They both are conceptually very similar. So, as we can see, Word2Vec uses a shallow neural network. It's shallow because it only has one hidden layer, so it's not deep learning, actually. And in this architecture, we have one input layer, we have one hidden layer, and one output layer. So it's really as simple as it gets, actually, or almost as simple as it gets. And what the SIBO algorithm then says is, all right, you have a piece of text. And from that piece of text, or maybe you have a corpus, a very large corpus of text, anyway, from that text, you start randomly sampling a word, right? You randomly sample a word. In our example, we have the sentence, intelligent machines control humans, and from that, we randomly sample the word machines. And our network will learn to predict this randomly sampled word that we also call target word. Then step 2 is, take the context, the n surrounding word of that target word. So in our example, that's intelligent, control, and humans. That's our context of machines. And we're going to use these context words to predict our target word. And that's what our network is going to learn. Our neural network is going to learn to predict a word given the surrounding word, given its context. And when you think back to the distribution hypothesis, well, that's what it says, right? You infer the meaning of a word based on its context. So it actually really models the idea of this hypothesis, which is 60 years old, so quite fascinating there. Well, and you keep doing that, right? You train your network. You just keep doing that. You keep randomly sampling words. You keep taking the context words, and you're training your network. You're evaluating your error at the output stage. You're taking the gradient of the error and propagating it back through the network. And by that, you're updating these weight matrices here. Since it's an optimization process, right, we're just trying to find the minimum or maximum of a function, and our function in our case is a loss function. And in this optimization process, we want to find the optimum set of weights here in these two weight matrices. And once we found that, once our training has converged, which means our network is not improving anymore significantly, well, we have this very interesting converged W prime matrix here. And Mikola found out that, well, in this W prime matrix, each column corresponds to a word, because that's the way this network is set up. If you want more details, we can discuss after that, or you look it up in the paper. It's not that easy to digest, but it's still OK. Anyway, you get this vector of a word. Each column of this matrix is a vector of a word. And he found that this word vector that we call word embedding actually encodes the true meaning of a word. And well, that sounds like magic now, right? Well, and it is a bit abstract, right? How can a numeric vector encode the true meaning of a word? That sounds strange. Anyway, let me give you a feeling of how this method, how these vectors encode the meaning of a word. When you look at this graph, right? Essentially what we did is we used TSNE, which is an unsupervised dimensionality reduction technique that is commonly used for reducing the dimensionality of high-dimensional vectors to make them, as in our case, to project them to two-dimensional space to be able to visualize them properly, right? So the words you can see here are vectors, actually, just now in 2 dimensions, so they're only points in two-dimensional space. These are vectors, and the arrows between them, they are the distances between vectors. And, well, when you, for example, look at the very left here, you can see that words that refer to animals are actually very close together. And that's because their resulting word embeddings are very similar. And when we speak of similarity in the context of vectors, we usually refer to cosine similarity. That means that the angle of these vectors is very similar. And that's the one thing how word2vec encodes the meaning. Similar words have similar vectors, so when you plot them, when you visualize them, they will be close together. And the other way it encodes context is that it also models the relationship between words. And that's quite interesting. For example, to the left on here, you can see that the distance between countries and their capitals is always roughly the same and always has roughly the same angle, right? That's how word2vec encodes the meaning of words. Great. So we can take a tick on the first part of this talk. We have actually gotten a really rough overview of natural language processing. We went from the very simple bag of words model that is just also incredibly ignorant to the quite sophisticated state-of-the-art word2vec text embedding algorithm. We saw that encoding semantics is the key to making machines truly understand what we mean, right? So that's it with the natural language processing part for now. Now we take a step to the side, and we're going to dive into recommendation systems, because that's the second part on our way to building a hybrid filtering recommendation system that is based on word2vec. So remember, we were just talking about text embedding algorithms. We said that word2vec is excellent at extracting the true meaning of a word, right? And it does so, by looking at the context, and if the context is similar, the meaning of 2 words is similar, right? And that's why it's going to generate similar vectors. That's how it works. And it turns out similarity is not only important when it comes to words, right? But it is actually a concept that's really everywhere in our lives. For example, when you think of social relationships, right? Similarity is incredibly important. There is this saying that you are the average of the 5 people you spend the most time with. And typically also your friends are highly similar to you. You usually share similar values, and also you very often like similar things. And that's where recommendation systems come into play. The keyword like. Recommendation systems also use similarity scores, right, to find out what you may like. And they do so in 2 different ways, in 2 basic different ways. On the one hand, there is collaborative filtering, and on the other hand, there is content-based filtering. In collaborative filtering, the systems look at the behavior of users. This means that, for example, you're a news website, right? And you have 2 website visitors, user A and user B. And they read mostly the same articles. So they have shown similar behavior, and then consequently, you assume that since they have a similar behavior, they also like similar things. And that's why you would recommend an article that user A has read to user B. That's collaborative filtering at its very basics. On the other hand, there is content-based filtering. In content-based filtering, we really do not care about behavior, but we focus on content. That's what the name says as well. And the way we do this is that we generate profiles of the elements in our system. So, for instance, we are a news website again, and the elements of our systems are items and users. So when I want to generate an item profile, what I do is I try to extract structured information from these news articles, which are my items. And the way I could do that is, for example, I could write down the author, the number of words in that article, or also the category this article belongs to, such as politics or economics. And then when a user comes to your website and reads an article, your system would then check which other articles have a similar profile to the article he's currently reading, and you would recommend the most similar article based on the profile to that user. Right, that's content-based filtering. So as you can see, on the one hand, collaborative filtering, we focus on the behavior of users, and on the other hand, we have content-based filtering, where we focus on the content of the elements of our system. Well, but these 2 are basic approaches. So, as it's always the case with basic approaches, they are faulty. They have problems, they have weaknesses in many ways. And well, it's the same with collaborative and content-based filtering. It turns out the collaborative filtering is suffering a hard cold start problem. That means if a user has only read 1 news article on a website, well, there is not much behavior information, right? How are you going to make a proper recommendation? And then also, you have the problem of synonyms. In collaborative filtering, even if you have 2 items that are practically identical, let's say duplicate news articles on your news website, collaborative filtering treats them as entirely distinct items in your system. And that's intuitively quite wrong. And then there's also the gray sheep problem. Gray sheeps refer to users that just do not behave like other users behave. They are these outliers in your data. And if, well, a user doesn't show any behavioral pattern that kind of is similar to any other user, you cannot make proper recommendations again, because you're dependent on behavior. Content-based filtering isn't dependent on behavior, so it has totally different problems. One problem is that it relies on the quality of the metadata you have. So let's say if you just don't know who the author is of some articles, or if you can't categorize it well, or you don't have mutually exclusive categories or whatever, right? You cannot make your item profiles in a good way, so your recommendations will be of poor quality. And then also, content-based filtering systems are quite infamous for making boring recommendations. And with that, we mean that, well, if you're reading an article about skiing, the content-based system is just going to keep recommending you articles about skiing, but it's never going to give you an opportunity to explore other areas, such as, let's say, Formula 1 racing or whatever. So that's kind of boring. It's very homogeneous recommendations. Well, as humans, every time we are really annoyed by problems, we come up with solutions. And it's the same with this. People were really annoyed by the problems of collaborative and content-based filtering systems, so they started to combine them. They started to make hybrid filtering systems. And a hybrid filtering system, per definition, is just any combination of a collaborative and a content-based system. And the goal of that is to overcome the specific problems associated with both of these basic approaches. That's actually hybrid filtering. And that brings us to part 3 of this talk. It brings us to us building such a hybrid filtering system that is actually powered by Word2Vec. That means we're putting together these very different fields. We're putting together recommendation systems as natural language processing to create, well, let's call it the Champions League of recommendation systems, hybrid filtering systems. But still, at this point now, we still feel that we are really far away from putting the parts together, right? I mean, we've heard a lot about natural language processing. We went from the bag of words model all the way to text embedding algorithms in Word2Vec. And then we went to recommendation systems. We saw that there was collaborative and content-based filtering, right? They have problems, and you can combine them to hybrid filtering systems. But that's all we've heard so far. So it feels like it's still a big step to actually build such a system. Actually, the step is not big. We have everything we need. We just need to put these parts together in the right way. And that's actually something that is absolutely not obvious. And it's something that even took researchers some time to find out. But it's also something quite fascinating. So in order to make this, to take a shortcut, to make this clear to you in just 2 or 3 slides, let me ask you a rhetorical question. Ask yourself, what do news articles and website visitors actually have in common? And well, the answer is really not obvious. That's why I called it a rhetorical question, because I will provide you with a solution as well. The solution is, well, they are both sequences. News articles are sequences and website visitors are sequences. Right? It's not right. I feel there are lots of question marks. Why are news articles sequences? Why are website visitors sequences? Well, I tell you, they are sequences, but it's a matter of perspective. When you take the perspective of a website visitor, a news article is, at its very core, a sequence of words, right? Just the same as a book. A book, at its very core, is a sequence of words. And similarly, for a website visitor, right? From the perspective of a news website, a visitor on my website is simply a sequence of page requests or a sequence of articles that user has read. So, as you can see, we can model both of these things, both a user and an article, as sequences. And that's actually something quite fascinating. And that's where the parts are starting to really go together. Right? Because we can take this thought one step further. If users are sequences of articles, and articles are sequences of words, well, then actually users are just sequences of words, right? I mean, this is an equation. It works. That means we can basically model a user in the same way that we can model an article. And that has some significant benefits that we will see later on. So our example user here now is simply a sequence of words. Well, a sequence of sequences of words, a sequence of the articles that user has read. Well, and now things look different. Now we get the feeling of how we can actually apply Word2Vec to that, right? Because Word2Vec, it's good at extracting the true meaning of words. So, and now we actually model all our elements of the system with words. That's where things are starting to work out. Because now, what we can do is, we can take a Word2Vec implementation, or we can do it by ourselves, and train it on our entire text corpus. So, when you're a news website, right, you just take all your news articles, let's say you have 1,000 news articles, you train your Word2Vec model on that, and it's going to give you a vector for each word. Well, but we're not interested in vectors of words now, right? We want to have vectors of articles and users to compute similarity measures to make recommendations. Because remember, we say the recommendation systems compute similarity measures to make recommendations. So we need to take some aggregation steps. Luckily, since we're dealing with numeric vectors, and they have some nice properties, because you can just make any mathematical operation on them, we can perform quite simple aggregation steps to get vectors that represent articles and vectors that represent users. And here you can see a very basic aggregation step. That's really just computing the centroid of vectors of words that appear in an article. That's going to give you the article vector. And similarly, the aggregation user level is just computing the centroid of vectors of articles that the user has read, and that's going to give you a vector for a user. These are very basic aggregation methods, right? You could think about anything here. You could think about weighting word vectors depending on TF-IDF scores, for example. You could think of weighting article vectors depending on the dwell time of a user, depending on whether a user bookmarked the website, and so on. So this is really very flexible, and here you just see the very basics of how this can be done in a simple way, but still you will see that the produced recommendations still have a very high quality. Great, and at this point, actually, we know everything that we need to build such a solution. And that's the next step. Since I was asked to show some code, we will be going through some code. I prepared a small Jupyter notebook. So for the people that are not familiar with Python, a Jupyter notebook is just a kind of IDE that in a notebook style, so it's quite nice for showcasing things, for doing exploratory analysis. You can find the notebook on our Craftworks GitHub account under github.com/craftworksgmbh/WAD. The notebook is self-contained. This means that everything you need to do exactly what we see here now is in this notebook. You can execute it by yourself. You can play around with it, do whatever you want. Also, the data is publicly available. I need to change. Why is there no signal technique? Well, some technical difficulties. Now it seems to be coming. Great, yes. There comes the Jupyter notebook. The data is publicly available. So we took data from Kaggle to actually enable everyone that's interested in it to do everything we do here by ourselves. The link to the data is also in the notebook, as you can see. So in this notebook, we will actually go from the very basics, from taking raw articles, from taking raw user article information, all the way to making recommendations. So since our time is quite limited, right, we only have like 15 more minutes, we will go over some parts of this notebook more quickly. These are the not so important parts for the topic of this talk. And over other topics, we will go a bit slower. And these topics will especially be Word2Vec and the recommendation system part. Right? So first, of course, we need some packages. We're just importing some packages, defining some variables and some paths. And now we are loading the data. And this is the first time we actually see what the data looks like that we're dealing with. And this is like the typical data that really fits perfectly to the problem I described in the slides. So what we have is we have a timestamp. And we know that at this point in time, a user that is defined by this person ID, which is a unique user identifier, has viewed, that's the event type, an article. Now I need to scroll down a bit. Yes, the article is defined by this title. The title is also at the same time the unique identifier of the article. And we have corresponding article text, which is just a very large string that really contains the entire article text. And yeah, it's under the variable text. So we have everything we need. We know which user read which article at which point in time. And we know the title of that article, and we know the text of that article. So really everything we need to go the entire process. Altogether, we have around 2,000 articles in our data set and around 1,600 users. So it's not, of course, a massive data set since nobody got time for that, right? And this is what such an article text looks like. It's really just a large string. And you know, in NLP, every time you face a large string, you know what you do. You pre-process it. You apply some tokenization, you know, some lowercasing, removing special characters, all that stuff, so that you end up with a list of strings. That's a more comfortable format for us. Right, so now we already have this sequence of words. Next, we just set up some dictionaries that map
that map titles, which are article unique identifiers, to the words occurring in that article, and users to articles that they have read, so users to lists of titles that these users have consumed. Right, that's what we are doing here. I know it's too quick to actually follow the code probably, but anyway, that's why you have the link to look into it in more detail if you want to. And now actually, we already have everything we need, right? We have our article text, we have them pre-processed into sequences of words. So now we're actually at the stage where we can train our word-to-vec model. Where we could train our word-to-vec model. Because we are smart, we do not train that model by ourselves, right? We only have 2,000 articles in this corpus. That's not enough data to get a decent word representation, probably. So what we are doing is we are using another very nice property of word-to-vec models, and that is that there are always tons of pre-trained models online. And these pre-trained models have been trained on very large data sets, on entire English Wikipedia dumps, on very large Google News corpora, and so on. So on the one hand, there is the advantage that we do not need to invest time into training this model, right? On the other hand, there is the advantage that since they have been trained on large corpora of text, the representations they provide us are very likely to be of superior quality to whatever we could produce with our rather small corpus. So we are loading a pre-trained model. The link to the model is also in the notebook. And that model we are loading is an object that can be essentially treated like a dictionary. We can query it with a word, and it's going to provide us with a dense numeric vector that represents this word. In our case, our pre-trained model provides us with 300-dimensional vectors. Usually the sizes of word-to-vec models, the size of word embeddings are somewhere between 50 and 300 dimensions. Depends on how complex your corpus is. Great. So next, we're actually performing the aggregations. So now we have our word vectors, right? Now we want to aggregate them. We want to get the article vectors and user vectors. So that's exactly what we're doing here. That's what this function is doing. It's simply computing the centroid of vectors of words that occur in an article, and it computes the centroid of vectors of articles that a user has read. So we get article and user vectors. Not more, not less. And since we have vector representations of all the elements of our system now, well, we can start making recommendations because we can compute similarities, right? And that's what recommendation systems do, at least memory-based ones. And that's what we're going to do now. And for that, we're going to use, again, this small helper function that basically just makes this similarity search more comfortable. It's since we have a very small data set, we can just do a brute force similarity search, and it's going to be done in a fraction of a second. If you have large data sets, you need to probably insert another abstraction layer, because then brute force searches are never a smart thing to do. Otherwise, this function also allows us to make 3 different kinds of recommendations. It allows us to make user-to-user recommendations. That is, we provide a user ID as input, and it's going to search for a user with a similar vector to that input user. Item to item is the same, just with items. Item to user is that you provide a user, and it provides you with similar items to that user. That's the 3 kinds of recommendations we can do. Great. So as a first step, we're going to look into user-to-user recommendations and the quality of these recommendations. To assess the quality in a qualitative way now, what we do is we just randomly sample a user from our user database. And that user is identified by this ID here. And well, as a first step, we just have a look at his vector, right? We said that these users are represented by 300-dimensional dense vectors. And that's actually the proof. It's 300 numbers in an array. There is the vector. And this vector essentially tells us what you can see here. These are the 7 articles that user has read. The article titles, right? We cannot see the text now. And we can see that this user is very interested in machine learning, deep learning, of course, and web apps, and also web apps. And this vector we see up here actually encodes this interest. Right. And as next step, we're going to use our helper function to find the 10 most similar users to that user. And that's what it gives us. It gives us the 10 most similar users. At the left, you can see the user IDs of these users. At the right, you can see the similarity score. As I said, we're using cosine similarity, which is defined to be between 0 and 1. So yeah, it's about 0.995 is a very high similarity. And this most similar user would be the user that we would base our recommendations on, right? So let's have a look what this most similar user here is actually interested in. These are the articles that user has read. And as we can see, it's also that user is very much interested in machine learning, in deep learning, and also a bit of Java programming. So the recommendations we would derive from these user, for our randomly sampled user, would actually be a quite good fit for his interest, right? So user-to-user recommendations, well, they work, obviously. Next step is item-to-user recommendations. So we again use our randomly sampled user and look for the 10 most similar items. And as we can see, these 10 most similar articles, well, they're all about machine learning, again, deep learning, and web programming. So also item-to-user recommendations work extremely well. The third part, last but not least, is item-to-item recommendations. In this case, we need to randomly sample an item, which is our article, Wall Street Goes Big on Bitcoin tag. And we're going to check which are the 10 most similar articles to that article, and whether these articles come from a similar area. And the 10 most similar articles are all about some combination of Wall Street, investment banking, and cryptocurrencies, blockchain. So it's really, also that really works out very well. Great. So we have seen that the quality of prediction is quite neat, right? And that it's quite simple to go from scratch, if you have a nice data set, to getting these predictions. So it's also really no magic. And another very nice property of this method is that you can actually visualize your vectors. You can get an intuition of how your recommendations actually work. And that's the last part of this notebook. We are again using TSNE, this dimensionality reduction technique, to project our vectors into two-dimensional space and visualize them. All right, and that's what you get. You get a lot of dots. And the blue dots are users, the red dots are articles, and the green dots, you can see down here, are also articles, but I marked the articles where the word blockchain occurs in. And what you can see is that articles that are similar, that have a kind of similar topic, are close together. Also, in a production system, right, this would not be a static picture, of course, but with every user that reads an additional article, the corresponding dot would move. So in a production system, this entire picture would be moving, and based on the movement of all elements of the system, recommendations are continuously changing. So it's really a self-learning, self-contained system. Great, so that's it with the notebook. Let's see if the technique works now. Yeah, looks good. We're just not going to start from the beginning again. So now you probably ask yourself, why would I actually want to do that, right? Why would I go through all this hassle to build that system? Well, there are a variety of reasons. There are a variety of advantages that this system has. Are we almost there? Almost. Oh, that's too far. There we are. So what do we get from that? We get quite some things. First of all, we get flexibility. And that's because we are mapping users and items into the same space. As we've seen, we model both of these elements of our system using words, right? So they are essentially, users are just really, really long articles. And so we can not only compare users and users, right, user to user, and not only item to item, but we can also do item to user recommendations. And that's really something quite neat, because that's also something very efficient. You do not need to search the entire user space for finding something similar, but only the item space, and item spaces are usually a lot smaller than user spaces. Also, in an item to user case, you do not need to store past user item interactions. Because what you do is, every time a user reads a new article, you just add up the article vector. For example, you add it up, you could do various things, to that user vector. So you would change the user vector depending on that user's behavior, but you do not need to actually store that interaction. It doesn't interest you anymore after that. And then last but not least, well, this approach overcomes a variety of problems of previous methods, right? We do not have a cold start problem anymore because we do not only use behavior, we also use content. And that makes the cold start problem a lot less severe because we're using a lot more information from our user to make our recommendations. We do not only look at which articles has this user read, but we look at every single word and what this word means when a user reads an article, right? And that's quite fancy. And then the synonyms, right? This method treats synonyms the way synonyms should be treated. If there are two identical or very similar articles, they will just have an identical or very similar vector. And that's what they are synonyms. Next, the gray sheep problem. We said the gray sheep problem is the issue that you face when a user just doesn't behave like other users. For example, a user reads articles that just nobody else has read. In a collaborative filtering setting, when you just look at the behavior of users, well, that is a problem. But since we are, again, looking at the content, at its very, very core elements, at each single word that user has read, this problem is not it's not very strong for us, since we have a lot more information, again, similar to the cold start problem, right? If a user reads very strange articles nobody else reads, there will still be words that are very similar to words that appear in other articles, and therefore we will be able to make decent recommendation to that guy. Last but not least, the problems of content-based filtering systems. Similarly, we do not rely on metadata, at least not entirely, since we're also using behavior information. You can even build entire collaborative filtering systems by using Word2Vec, right, without relying on any metadata. And also, we do not necessarily make boring recommendations. As we've seen, we can make user-to-user, item-to-item, and item-to-user recommendations. And as we've also seen, user-to-user recommendations are typically more heterogeneous, right? And item-to-item recommendations are typically quite homogeneous. So with our approach, we are flexible. We can actually choose the level of boringness you want to have in a recommendation, basically. Great. So we've covered a lot now, right? And as I said, we only have 2.5 minutes left. That's perfect. We covered first natural language processing, right? We saw that NLP has become an incredibly ubiquitous technique. It's everywhere. It's powerful. We went from the bag of words model all the way to word embeddings, to text embedding algorithm, by understanding how important it is to capture semantics. And then we took a step to the side and we discussed recommendation systems. We saw that recommendation systems compute similarity measures to make recommendations. They do so in two ways, collaborative and content-based filtering systems. Both systems have weaknesses, so we build hybrid filtering systems. And that's how we ended up at our last point, how we can actually really build that, and how this works in practice, and what the nice properties of these systems are, right? That's how we ended up here. And remember, you can find the notebook online as well. Great. Thank you very much for your attention. If you have any questions, right, since we are out of time, as I expected and announced, I will be here. We have a coffee break of 15 minutes, so you can ask any question that may have popped up. I will leave no question unanswered. Furthermore, if you have any questions about what we do at Craftworks, please visit our website, or just also talk to me or send me an email. Great. Thank you very much for your attention.